The concept of time travel has captivated the human imagination for centuries. From H.G. Wells's iconic The Time Machine to countless science fiction films, the allure of journeying through time has fueled our dreams and challenged our understanding of the universe. But is time travel merely a product of our imagination, or could it be a real possibility grounded in scientific principles? While the technology to travel through time remains elusive, the theoretical frameworks of modern physics suggest that time travel, at least in principle, may not be as far-fetched as it seems. The scientific exploration of time travel begins with a fundamental question: what is time? Our everyday experience suggests that time flows linearly and unalterably, always moving forward. However, the groundbreaking work of Albert Einstein in the early 20th century revolutionized our understanding of time, revealing it to be a much more complex and malleable entity than we once believed. Einstein's theories of special and general relativity shattered the Newtonian notion of absolute time, demonstrating that time is not a universal constant but rather a relative quantity that is intimately intertwined with space. This revolutionary insight forms the foundation for our current scientific understanding of time and provides the theoretical basis for the possibility of time travel. To comprehend the complexities of time travel, we must first discard our intuitive perception of time as an independent and absolute entity. Einstein's theory of special relativity, published in 1905, unveiled a profound and counterintuitive truth. Time is not absolute but relative. The rate at which time flows depends on the observer's relative motion. This means that time can pass at different rates for observers who are moving at different speeds relative to one another. Imagine two identical clocks, one stationary and the other moving at a high velocity. According to special relativity, time will pass slightly slower for the moving clock compared to the stationary one. This phenomenon, known as time dilation, has been experimentally verified countless times and is a cornerstone of modern physics. Time dilation implies that time is not a rigid, unchanging backdrop, but rather a flexible dimension that can be stretched and compressed by motion. Einstein's theory of general relativity, published in 1915, further deepened our understanding of time by revealing its intimate connection to gravity. General relativity describes gravity not as a force but as a curvature of space-time, a four-dimensional fabric woven from the three dimensions of space and one of time. Massive objects like stars and planets warp the fabric of space-time around them, much like a bowling ball placed on a trampoline. This curvature of space-time is what we experience as gravity. One of the most intriguing theoretical concepts that could potentially enable time travel is the wormhole. Wormholes, also known as Einstein-Rosen bridges, are hypothetical tunnels that connect two distant points in space-time. Imagine folding a piece of paper in half and then poking a hole through the folded layers. The hole represents a wormhole, providing a shortcut between 2 points on the paper that would otherwise be far apart. While wormholes are consistent with the equations of Einstein's theory of general relativity, their existence remains purely theoretical. Physicists have yet to observe a wormhole directly, and their formation and stability pose significant theoretical challenges. One major challenge is that wormholes are predicted to be incredibly unstable and prone to collapsing faster than the speed of light, making it impossible for anything to travel through them. To keep a wormhole open and traversable, physicists have proposed the existence of exotic matter, a hypothetical form of matter with negative mass energy density. While no evidence of exotic matter has ever been found, its existence could potentially stabilize wormholes, preventing them from collapsing and making time travel through them a theoretical possibility. Another theoretical avenue for time travel involves manipulating the very fabric of space-time itself. According to Einstein's theory of general relativity, gravity is not a force but rather a consequence of the curvature of space-time. Massive objects warp space-time around them, and this warping is what we experience as gravity. If we could somehow manipulate the curvature of space-time, we could theoretically create shortcuts through time, allowing us to travel to the past or future. One hypothetical method for achieving this is by creating a warp drive, a concept often explored in science fiction. A warp drive would work by compressing the space-time in front of a spacecraft while expanding the space-time behind it, effectively creating a warp bubble that propels the spacecraft at faster-than-light speeds. While the concept of a warp drive is highly speculative and faces immense technological hurdles, it is not inherently ruled out by the laws of physics as we currently understand them. Some physicists have proposed theoretical frameworks for warp drives, such as the Alcubierre drive, but these concepts require the existence of exotic matter, the same hypothetical substance needed to stabilize wormholes. While traveling to the past remains a highly speculative possibility, traveling to the future is a well-established phenomenon within the framework of special relativity. As mentioned earlier, time dilation dictates that time slows down for objects moving at high velocities relative to a stationary observer. The faster an object moves, the slower time passes for it relative to a stationary observer. This means that if we could travel at a significant fraction of the speed of light, we could effectively fast forward into the future. For example, if we were to board a spaceship and travel at 99% the speed of light for 1 year, upon returning to Earth, we would find that many more years had passed on Earth than had passed for us on the spaceship. This is because time would have slowed down for us relative to Earth due to time dilation. While we currently lack the technology to travel at speeds approaching the speed of light, time dilation is a very real phenomenon that has been experimentally verified countless times. For instance, atomic clocks flown on airplanes have been shown to tick slightly slower than their counterparts on the ground, albeit by a minuscule amount due to the relatively slow speeds involved. The prospect of time travel, while tantalizing, raises a host of perplexing paradoxes that challenge our understanding of cause and effect. Perhaps the most famous of these is the grandfather paradox. Imagine a scenario in which you travel back in time and accidentally kill your grandfather before your parent is even born. If your grandfather died before your parent was conceived, how could you exist to travel back in time in the first place? This paradox highlights the potential for logical inconsistencies that arise when we consider altering the past. Another mind-bending concept is the butterfly effect, which suggests that even small changes to the past can have significant and unpredictable consequences in the future. The classic example is that of a butterfly flapping its wings in Brazil, potentially causing a tornado in Texas weeks later. This concept, rooted in chaos theory, highlights the interconnectedness of events and the difficulty in predicting the long-term consequences of altering the past. While these paradoxes present formidable challenges to our understanding of time travel, they do not necessarily rule out its possibility entirely. Some physicists have proposed solutions to these paradoxes, such as the Novikov self-consistency principle, which posits that any actions taken by a time traveler in the past were already predetermined to occur, thus preserving causality. While time travel remains largely in the realm of theoretical physics, several areas of active research offer tantalizing clues and potential pathways towards a deeper understanding of this enigmatic concept. Quantum entanglement, one of the most bizarre and counterintuitive phenomena in quantum mechanics, involves the instantaneous correlation of two or more particles, regardless of the distance separating them. This spooky action at a distance, as Einstein famously called it, has led some physicists to speculate about potential connections between quantum entanglement and wormholes, suggesting that these entangled particles might be connected through microscopic wormholes. Another area of active research focuses on conical singularities, also known as cosmic strings. These hypothetical one-dimensional topological defects in spacetime are predicted to have immense gravitational pull, potentially warping spacetime in their vicinity significantly. Some physicists have theorized that the intense gravitational fields surrounding cosmic strings could be harnessed to create closed time-like curves, paths through spacetime that loop back on themselves, effectively enabling time travel. In addition to these avenues, researchers are also exploring paradox-free models of time travel, attempting to reconcile the theoretical possibility of time travel with the preservation of causality. These models often involve concepts like multiple timelines or self-consistent loops, where any changes made to the past are already woven into the fabric of spacetime. While the technology to travel through time remains firmly in the realm of science fiction, the ongoing exploration of time travel's theoretical underpinnings continues to push the boundaries of our understanding of the universe. Further research into quantum entanglement, wormholes, warp drives, and paradox-free models could potentially yield groundbreaking insights leading to technological advancements that were once thought impossible. The implications of time travel, if it were to become a reality, are as profound as they are difficult to fathom. The ability to journey through time would revolutionize our understanding of history, allowing us to witness pivotal events firsthand and potentially even alter the course of human events. However, the ethical and philosophical ramifications of such an ability are significant. The potential for altering the past or future raises profound questions about free will, determinism, and the very nature of reality itself. The quest to understand and potentially conquer time has been a driving force behind scientific inquiry for centuries. From the groundbreaking theories of relativity to the exploration of exotic concepts like wormholes and warp drives, the pursuit of time travel has led to profound advancements in our understanding of the universe. While the technology to build a time machine remains elusive, the ongoing exploration of time travel's theoretical foundations continues to inspire new generations of scientists and fuel our collective imagination. Whether time travel will forever remain confined to the realm of science fiction, or eventually transition into the realm of scientific reality, remains an open question. However, the journey itself, marked by groundbreaking discoveries and mind-bending thought experiments, has already enriched our understanding of the cosmos and the nature of time itself. The pursuit of time travel is ultimately a testament to the boundless capacity of the human mind to question, explore, and push the boundaries of the unknown.